All right, so this is Chapter 6. We're going to start Lecture 6, Part 1. This chapter concerns the treatment of analytic geometry. And we're going to start off with a discussion of conic sections. Make sure I've got the tool shared out. Okay, yeah, so we're shared. Okay, so what a conic section is, they're formed in the following ways as shown in this illustration. If you take two cones and you line the cones up so that they're perpendicular to each other at the vertices, at the apex of the cones, then what happens is a circle is formed if you take say a slice of the bottom cone, where this plane that slices through the bottom cone is parallel to the base of the cone. And if you tilt this slicing plane from the horizontal slightly, then the inscribed figure, as shown in the second figure, is an ellipse. So an ellipse, of course, would be the portion where the slicing plane intersects the cone. And the circle, of course, is where the slicing plane intersects the cone when the slicing plane is parallel to the base of the cone. If you were to take the slicing plane and extend the slicing plane through the base of the cone and coming out, say, the wall of the cone, on the side of the cone, then the intersection of the slicing plane and the cone would form a parabola. And then the reason why we need two cones is so that we can form a hyperbola, and that is when you take the slicing plane and slice it through the two cones, and the slicing plane is perpendicular to the base of the cone. And then where the slicing plane intersects the two cones, you have essentially a hyperbola. So the first conic section we're going to talk about would be components of a parabola. So first of all, we'll give a review definition of what a parabola is. So one second while I pull up the picture. I guess I could leave it there. Okay. All right. So in this illustration, what I'm going to show are basically what essentially is the definition of the parabola. So a parabola is a set of points in the plane, in the XY plane, equidistant from a fixed point, F, called the focus, and a fixed point line called the directrix. Okay. So what you have is the locus of points. A parabola is the locus of points that are equidistant from F, okay, called the focus, this point in the XY plane, and a straight line called a directrix. So if you choose any point in the XY plane, say right here, okay, then calculate its distance to the directrix, this line, okay, and then calculate the distance between the focus and this point. And if they're equal, then that point will be on the parabola, okay? And so you'll have an infinite set of points which are equidistant from F and L. So the vertex of a parabola, of course, is the point on the parabola that exhibits shortest distance to the focus and shortest distance to the directrix. All right, so that's the fundamental definition. So yeah, here's your point P. So here's two examples of a parabola, of course, where I guess I should give you the fundamental equation. A parabola, of course, is defined by the quadratic equation ax squared plus bx plus c. And I believe if you go back to your Lecture 1 notes, Chapter 1 lecture notes, I gave you a procedure known as completing the square for calculating the coordinates of the vertex or a parabola. And we know that if the leading coefficient of the parabola is greater than 0, then the parabola opens up in the xy plane. And if the leading coefficient of the quadratic formula, A, that is less than 0, then you know that the parabola opens down. And then we have the axis of symmetry, which is a vertical line that passes through the vertex, like so. All right, so with this new definition, or with this other alternative definition of a parabola, being the set of points in the plane equidistant from a fixed point F, the focus and the directrix, then we need not necessarily always have parabola which open up or down. They can open up to the left or to the right. All right, so So we have a couple of constructions we can make. I can start off by saying let P, x, y, right here, be on the parabola, and the distance from the point to the focus, of course. If we decide that the vertex, if we place the vertex at the origin, so this could be, say, like y equals x squared. So let's consider the case y equals x squared. All right. So the distance from the point to the focus would be the square root of the distance of the abscissa squared, the distance between the two abscissas squared, plus the square of the distance between the ordinate of P and the ordinate of the focus. Okay, and so this would be the distance from point P to the focus right here. Now the distance from point P to the directrix, okay, so what would that be? Well, that would be, let's see if we can calculate that out. That would just be, okay, so that would be this distance, right? That would be simply this distance. That would be y. Okay, so they call this our directrix. Okay, so if this is our directrix, then the distance from P to the directrix is just merely the absolute value of y minus P, since the abscissas are the same. Okay, so the distance from a point to a horizontal line is just merely this. Okay, and so that would equal to the absolute value of y plus P. All right, and so obviously we want to equate these two distances. So by definition, then we have what? We have the following results. The distance from an arbitrary point on the parabola y equals x squared to the focus then is x squared plus y minus P quantity squared, and that has to equal to the absolute value of y plus P. Okay, which of course we know by definition of absolute value, that's just the square root of y plus P quantity squared. Okay? All right, so now, so if we were to simplify this expression, squaring both sides, we would have x squared plus y minus P quantity squared is equal to y plus P quantity squared. And then we can complete the squares on both sides of the equation. So we would have x squared plus y squared minus 2yp plus p squared is equal to y squared plus 2yp plus p squared. Okay, and then what happens? The y squares will cancel, right? So y squares cancel. The p squares would cancel. And let's add 2yp to both sides. And if we were to do that, we would get x squared is equal to 4yp. Okay? And so this is an alternative form of the equation of a parabola. Okay? So the graph of, so what this means is that the graph of x squared equals 4 pi. Okay, so the graph x squared equals 4py. Okay, this is a graph of a parabola with vertex at the origin. Okay, and what else? It has a focus at the point 0p, and it has a directrix the line is y equals minus p, and if p is greater than 0, the parabola opens up. Okay, and if p is less than 0, the parabola opens down. P less than 0, parabola opens down. Okay, and you may have seen this in algebra. All right, so let me give you some examples. Pull up some graphic tools here. So in this case, consider the graph x squared equals 8y. So the focus, so if we were to have an understanding that 8x squared equals to 8x squared is equal to 8y, that is, which is equal to 4py, then solving for p, of course, p is equal to 2, which is greater than 0. So that means the parabola would open up. The focus would be at 0, 2, and the directrix would be at y equals minus 2. And so here's a case, the generalized case, with x squared equals 4py with p greater than 0. You would have this case, that is the vertex of the parabola is at the origin. And you can see that with the directrix, with p being greater than 0, the directrix occurs below the x-axis, and so the parabola opens up. And in this case, with p less than 0, the directrix occurs above the x-axis, forcing the parabola to open down. All right. Okay, so let's see what kinds of problems we can answer. All right, so how about find the focus and directrix. So let's do this. Find, and I'll find focus and directrix of the parabola of y equals minus x squared. Okay, well obviously this parabola opens down, so you would expect p to be less than 0 and the directrix to be above the x-axis. So the way you would proceed is x squared is equal to minus y, all right, which is equal to 4py. Okay, so solving for p, we require that 4p is equal to negative 1. So p is equal to negative 1/4. Okay, and that implies that the focus is equal to the point 0p, which is equal to 0 minus 1/4. And then the directrix would just be, so the directrix would be the line y equals negative p. Y is equal to negative p, which is equal to 1/4. Okay, all right, so that would be the answer to that question. Let's do the same for this equation. Do the same for 6x plus y squared is equal to 0. All right, so we have, okay, well in this case we need to, this isn't the form we just did, so this would be a case of a parabola opening up to the right or left. So I need to, before we answer this question, I need to give you another definition. So I kind of jumped the gun on this, so let me do so on the next slide, and then we'll solve this problem. Okay, so let me pull up the note. So parabola with horizontal axis. All right, so we have the following concepts. The graph of the equation y squared equals 4px is a parabola with the following properties. Again, the vertex will be at the origin. This time, however, the focus will be at p0. Focus will reside on the x-axis, and the directrix will be x equals minus p. And so if p is greater than 0, the parabola will, of course, open to the right, and if p is less than 0, the parabola will open to the left, as shown in these particular examples. Okay, so we're just interchanging the roles of x and y and the coordinate axes. So now, with this note, we can answer the question 6x. We can find the focus and directrix for 6x plus y squared is equal to 0. Okay, so proceeding, we can solve for y squared. We can put it in this format right here. So we have y squared is equal to what, minus 6x, which must equal to 4px. Okay, and so 4p is equal to minus 6, and that implies that p is equal to negative 3/2, right? So therefore, your focus would happen at negative 3/2, 0. And your directrix, of course, would be the line x equals 3/2. This is the directrix. Right? And to convince yourself this is true, I can show you the graph. So let me pull up the graph. All right, so the graph of that would look like this. So here's 6x plus y squared equals to 0. Here's your directrix, x equals to 3/2. Here's your focus at negative 3/2, 0. And so any point on the parabola, the distance from any point to the focus is the same as the distance to the directrix. So these two distances will be the same for any point. And then also I labeled the upper branch of the parabola could be considered y equals the square root of negative 6x. And the lower branch could be considered y equals the square root negative of the square root of negative 6x. Okay, so one of the things we can do is we can estimate the width of a parabola. So that's another interesting geometric concept. And oh, by the way, I'll show you later on how this all relates to trigonometry. There is a very keen relationship, but I want to get some terminology settled first before we jump into the trigonometry aspects of this. Okay, so the width of a parabola, what do we mean by that? So estimating the width of a parabola, it's a line segment that runs through the focus, okay, to the axis, from the line segment through the focus, perpendicular to the axis, okay, perpendicular to the axis with endpoints on the parabola, okay. Okay, so you've got this, what's called the lattice rectum. It's the length of the lattice, okay, so the length of the lattice rectum is called the focal diameter, and it's equal to the absolute value of 4p. So the length, or the width rather, the width of the parabola, in summary, is, okay, first of all, you construct this line right here, okay, and you have two endpoints on the parabola, okay, and it has to pass through the focus of the parabola, and it has to be perpendicular to the axis, okay, so it has to be perpendicular to the coordinate axis for which the focus resides on. So in this case, the lattice rectum has to be perpendicular to the x-axis for this particular parabola. And so the length of the lattice rectum is the absolute value of 4p, okay, because by symmetry it's 2p plus 2p. And this is also called the focal diameter, okay, so it's that distance. All right, so I guess we'll have some problems calculating that. And why do we want to calculate the focal diameter? All right, so let me show you a couple of examples as to why we would want to do this. Okay, I was just checking the notes to see how they're ordered. Okay, so view, rotate view. All right. So, for example, let's see here. Let me pull up the right problem. Yeah. So, knowing this parameter of a parabola, the diameter of a parabola, or the length of the latus rectum, is used a lot in optics, in the design of reflecting lights. So here's this example will demonstrate that. So, for example, let y equals 1/2 x squared, and then x squared equals 2y, which implies that p is equal to 4p is equal to 2, which of course is your focal diameter. So you have a focal diameter of 2. So that means your focal diameter would be, for this parabola, right here. This is your lattice rectum that I'm accentuating in green. Okay, so for parabolas, parabolas are used in reflector lamps and telescopes. And it turns out that light from a light source at the focus reflects off the parabola parallel to the axis of symmetry. And conversely, light approaching the reflector and rays parallel to the axis of symmetry is concentrated at the focus. So what happens is, if you've got like starlight coming in, okay, it hits the walls of the reflecting parabola, and then it bounces off the wall of the parabola and it hits the focus. All right. So depending on the calibration of the focus, you can detect faint light-emitting sources by concentrating the light from those sources at the focus. Likewise, if you want to emit a strong light, you just reverse the direction. You put a light source at the focus, and then the beams emanate from the focus and they bounce off the walls of the parabolic mirror, or a parabolic light source, and then they shoot out from all the various points on the walls, and then they have a stronger light source, such as in the case of a searchlight. So let's see an example of a searchlight type construction. So let me pull up that lecture piece. So here's a problem, an example problem that you may see in WebAssign. Okay, so for example, a searchlight has a parabolic reflector that forms a bowl 12 inches wide, 8 inches deep. Okay, so as shown in this figure. Okay, the light is located at the focus. How far from the vertex of the reflector is it? Okay, so you want to know how far from the vertex. Here's the vertex, is the light source of the reflector. Okay, so I believe, okay, so in order to do this, you take a cross-section of the parabolic reflector, okay, which is a parabola, okay, and we determine that, okay, so if it's 12 inches across, so by symmetry, we know that this distance is 12, right? And so we place the vertex of the parabola at the origin, like so. Okay, and so by symmetry, we know this distance to be 6. Okay, now if this is the xy plane, the generalized equation of the parabola with vertex at the origin opening up is x squared equals 4py. And so we already have a value of x. So 36 is equal to 4py. Now, when you're 6 inches this way, then we know that we're 8 inches from the vertex in the vertical direction. So we know this to be 8 inches. So therefore, from the diagram, we deduce that the properties of a parabolic cross-section will have this property. So 36 is equal to 4p times 8. So of course 36 is equal to 32p, so solving for p, p is equal to 9/8. So that's how far from the vertex the reflector, how far from the light source is, that is. So that's actually where the focus is. Okay, the focus is at p0 in this case. All right, so that's how you would design searchlights, and where to place lights and searchlights depending on the parabolic shape of the searchlight. Okay, so we can try another one. Let me see. Okay, this, I think, okay, let me pull this one up. All right, so let's see how this one works. Okay, so a reflector for a satellite dish is parabolic in cross-section with receiver at the focus right here. The reflector is 1 feet deep and 20 feet wide from rim to rim. Okay, how far is the receiver from the vertex? Okay, from the vertex of the parabolic reflector. Okay, so obviously the vertex of the parabolic reflector will be somewhere right here. Okay, so this will be the vertex. Okay, so to solve this, we assume we'll overlay a XY coordinate system. So this will be our y-axis. This will be our x-axis, like so. There's our vertex centered at the origin. So we know that x squared is equal to 4py. Okay, so if you work for GCI and you're having to install satellite dishes, probably be useful to know this. All right. So we know then that what? So we know the point, we know the coordinates of this point, right? Let's see. Well, actually, oh, I'm sorry. Maybe I misused the information. Perhaps this would be the directrix. I think maybe they're considering this the directrix. Okay, and then the red denotes the. Okay, so I'm sorry. So I don't have my x-axis drawn properly. Okay, so this is the directrix, and the red, okay, ostensibly is the outline of the parabola. Yeah, so we'll make this the surface of the parabola right here. So this point right here, right, so, okay, so our directrix then would be, okay, so we have, if we assume that, I'm trying to think, what do we assume the coordinates of this point would be? So 10, we know this to be x equals 10. And, all right, so if this is our coordinate system, all right, so let's make this a coordinate system. We'll call this x, the x-axis right here. And so, or it's hard to know. So parabola opening up. Well, maybe not. Yeah, the tricky part of this question is determining what the coordinate system is. So, So if we make this the coordinate system, okay, and so the coordinates of this point would be, so if we call this the y-axis. Now we're dealing with a physical device, okay? So that means that we could say, since this is a parabolic dish, we could say that the coordinates of this point, with respect to this being the x-axis, okay? We could say that y is positive in this direction, since we're dealing with a physical device. So we could say ostensibly that the point x equals 10, if this is the origin, okay, x equals 10, y equals 1 is on the parabola. Okay. All right, and so we have x squared is equal to 4py, so we'll have 100 is equal to 4 times p times 1, which makes p equal to 25 feet from the vertex. So p this would be my guess how to solve the problem. Okay. The vertex, as far as the receiver. Okay, so yeah. So the trick is to find a coordinate system for this that works. Okay, all right. Another one from astronomy. Let me pull it up. Okay, so let's see what we have here. Try again. Didn't want to paste. Okay, so hello, where's my drawing? It's not working. Well, I guess that isn't going to come up. Let me save it. File. Try it again. Copy, please. All right, I'll have to write it down because for some reason the cut and paste doesn't work anymore with this tool. All right, shoot, that's too bad. All right, the Hale telescope. At Mount Palomar. Observatory. It's the Mount Palomar Observatory. Has a 200-inch mirror. Okay, the mirror is constructed in a parabolic shape. It collects light from the stars. And focuses at the prime focus. Okay. The mirror is 3.79 inches deep at its center. All right. Find the focal length of the parabolic mirror. Find the focal length of the parabolic mirror. Okay, so in other words, the distance from the vertex of the parabola to the focus. All right, so what can we do with this? We can probably see if there's a useful picture. Okay, and then overlay a coordinate system. All right, so this problem we solved just like we did previous problem. So I have an illustration to show you. I think the paste is working now. All right, so consider this drawing. Okay, so here's a sketch of the Palomar Observatory telescope. And you can see that the red is the parabolic shape right here. And so we have, if we overlay our coordinate system, again, here's the vertex. So x squared is equal to 4py. And the parabola has to pass through the point 103.79 in this coordinate frame. So that means 100 squared is equal to 4p times y, which is 3.79. And so we can solve for p to get 659.63. So the receiver has to be, that is the focus, has to be 659.63 inches from the vertex. All right, so that's how far this is from the vertex. So this distance right here, roughly what, 12 inches per foot? So it'd be almost 55 feet. That's about a 56-foot length distance there. All right, so that's how you solve that. Okay, so that concludes our 6.1 lecture notes on parabolas. So 6.2 will cover ellipses.